Assalamualaikum everyone, and this is our new topic of chapter 3, Introduction to Root Locus. So this is the first video which is focused on introduction to the root locus. So lesson outcome of this topic. So upon completion of this topic, you should be able to define the root locus, sketch the root locus manually, and use the root locus to find the dominant closed loop poles, analyze the system using root locus, and finally, you should be able to design the cascade compensators, which is the lag and lead compensators. So as an introduction, so what is root locus? Okay, by words, root is mean that root of S polynomial equation, and the locus is mean set of points of the locus. Okay, by definition, root locus is defined as a graphical representations of the closed loop poles as the system parameters is varied. In this case is the gain, and thus it is a powerful method of analysis and design for stability and transient response. So this is the two focus that we will look into of this root locus topic. Okay, let's go further. So as an introduction, given this is the closed loop system, okay, with the gain K and GS as the open loop system. So given the characteristic equations of this closed loop system as this equation, 1 plus KGS equal to 0. So this characteristic equation is very important. Why? Because of the gain K. So as the variation of this gain K, it will determine the system response of the system, because we can see the trajectories of the root locus from the characteristic equation when this parameter K is varied from 0 to infinity. Okay. So now let's look. This is a security camera system which will automatically follow a subject, and the tracking system will monitor the pixel changes and position of the camera to the center of the changes, meaning that this camera will look into the changes of the pixels so that the subject position will also changes. Okay, so the root locus technique can be used to analyze and design the effect of loop gain upon the system transient response and stability. Okay, so the closed loop poles of the system change location as the gain K is varied. So in this case, the gain is K1 and K2. Okay, so once this gain varied, okay, by the subject positions movement, it will result in the varied of the camera position as well. So next, okay, as a same example, this is a closed loop transfer function system, and the first one is the open loop transfer function KGS HS. Okay, so the gain is K, which is K1 and K2, and this is the open loop system, okay, with the unity feedback HS. So we know that if the open loop transfer function, we know the stability of the system is depend on the poles. If the poles is lie on the left hand of the S-plane, so the system is stable. And if it is in the right hand of the S-plane, the system is unstable. But in the closed loop transfer function, as this given equation, the stability depends on the gain K. So how? Let's look into next slide. For example, this is the open loop transfer function. We don't have any zero here, but we have two poles here at minus 10. So we know that the system is stable. But for the closed loop transfer function, as this equation, we need to find the gain k, so that the system will stable or unstable. Okay, let's see further details on this. Okay, so the same example as this given equation. So now we vary this k. Let's say I put the k into the 1. Okay, so this is the system. The result will be over them. But if I vary the k to 25, the system will show critically damped. Same as k equal to 50, the system will become under damped. So we can see that the values of k changes will result in the location of the poles, and hence it will result in the system response. Okay, next. Now we see the further details on the pulse location and its trajectory. Also the same example. Okay, so first, the initial pulse location is -10 and 0. Okay, so this pulse we get from the characteristic equation of the closed loop system. So this is when the k is equal to 0, meaning that, so this is the first initial location when k is equal to 0. Once we vary the k, let's say I vary to 25, so the location of the poles will become at -5 and the same as poles here. So this is where it double at the same point. So this is where k is equal to 25. And again, the system again increase to 50. So the location of the poles will become at -5 plus minus j in here. So this is where k equal to 50. So we can see that the variation of k will affect the closed loops of the poles, and also this is what we call as a root locus. Okay, next, as a summary, when the gain k is equal to 25, meaning in the real axis point here, the system will become overdamped. At gain k equal to 25, which is in here, where the point of intersection between two poles, the system will become critically damped. Finally, when the gain more than 25, it will enter into the complex plane from left and the right, and then the system will become overdamped. So the root locus will allow us to make the association and will become an important technique and analysis of the higher order system. Okay, so the root locus properties. So now let's consider the second order system. So this is the gain and this is the open loops function. So the characteristic equations of this all closed loop system is given as this one. Okay, so this is the denominator of the closed loop equation. So we can find from this the denominator of characteristic equation, we can find the natural frequency omega n and also the theta or the damping ratio. Okay, so this is, we can know the effects of the system, and also we can vary these parameters for the system response. Before that, the root locus of gain k is varied, so we can find it by requiring these two equations. So this is the magnitude criterion, and this one is the phase criterion. So how do we know that the root locus is in the path of the system? So by looking at the angles of the complex number, if this found to be odd number of multiples of 180 degrees, then the value of S system is a system pole for some particular value of K. So let's see some example of these root locus properties. Example 3.1. So given a unity feedback system as in this figure 3.1, okay, so calculate the angle of GS at the point of -2 plus J3 by finding the algebraic sums of the angle of the vector drawn from the zeros and poles of GS to the given point. Then determine if the point specified in 1 is on the root locus or not. Okay, so this is the given closed loop system. So we can see that two zeros and two poles. Okay, so we want to determine whether this point is the point of the root locus or not. Okay, so let's see the solution. So first you need to find all the angles of the poles and the zero. Okay, so this is the phase criterion. Okay, so from the equation you replace S equal to -2 plus J3, S plus 4, and replace the S with -2 plus J3 and plus 4 here. So you will get 2 plus J3 and convert this complex form into a polar form. You will get 3.61 to the degree of the phase is 56.31. So what we concern is the phase. So the same as for the poles, the degree of the poles and the zero. So you will get the first zeros is -6.31 and 70.57. The next is minus the 19 degree and 108.43 degree. So use this equation to find whether the total sum of 0 minus with the total sum of poles. So you will get -70.55 degree. So this is not the odd multiple of 180 degree or 540 degree. So since this is not the odd multiple of 180 degrees, so therefore this point is not a point in the root locus. So this is not the point of the root locus. Okay, so you can use this link as well to calculate the phase criterion. So let's see example 3.2. So given a unity feedback system as figure 3.2 and calculate the angle of GS at the point -3 plus J0. So we want to find whether this point is the root locus point or not. Okay, so if the point is specified in 1 is on the root locus, we need to find the point. Okay, so and then if the point specified in 2 is on the root locus, find the gain K using the length of root locus. We have 1 0 here and we have a complex poles here. Okay, so let's learn. So convert the equation into the complex equation, and then we substitute S equal to -3 plus J0. Okay, so again we need to find all the angles of the poles and 0. So we have here 180 degree for the first 0, and then the poles we get this degree. Then by using this equation, we need to sum all the zeros and minus to the sum of the poles. Okay, so the answer will be 180 degrees. So we know that 180 degrees is the odd multiples of 180 degrees. So this point is the point of root locus. So what is the gain at this point? So by using this equation, so you can find the gain k of the equation by inserting all of the s into this equation. So you will get gain equal to 9.99 or 10. And this is the reference that you can see more details on the root locus method. So that's all for now. Thank you everyone.